Hello everyone. My name is Anil Subramanya, and I'm the General Manager for Amara Global's Enabling Futures program. Welcome to the third webinar in our series. Thanks for coming along. The Power of Positioning series of webinars have been really successful. We've run them over the last 2 weeks, and this is the final one before we lead into the workshop next Thursday on the 3rd of December, and we look forward to seeing you there too. The meeting will be, the webinar will be recorded, and we will make that available to participants at a later date, and we'll inform you when that's up and running. A brief introduction to Amara Global. We are a 60-year-old global research collaboration platform for it's a not-for-profit member-based organization that enables that collaboration between industry, researchers, SMEs, and government globally. You can go to our website, amara.global, to learn more about us. I'd also like to thank, before we kick off, Frontier SI, who partnered with us in bringing this series and the workshop together. Frontier SI brings together collaboration in the spatial industry, and you can read more about them by going to their website, or you could even go to the Amara Global website to see an interview with Graham Koenig, the CEO of Frontier SI, who's spoken in that interview about all things spatial and what's exciting about the future of positioning and spatial sciences. Now, without further ado, I'll introduce you to our next speaker, Nicholas Brown from Geoscience Australia. Nicholas has assured me he's fine that we call him Nick. So Nick is the director of the National Geodesy, co-chair of the UN GGIM subcommittee on geodesy, a member of the Intergovernmental Committee on Surveying and Mapping, chair of the ICSM Geodesy Working Group, and a member of the FIG Commission, Commission 5. Nicholas is responsible for the development and refinement of the Australian Geospatial Reference System, the collection of datums, geoid models, transformation tools, and standards required for 4D positioning. Nicholas has a Bachelor of Applied Science in Geomatics from RMIT and a Master's in Geophysics in Space Geodesy from ANU. I think we can all agree with that set of credentials. We've got an exciting speaker, a knowledgeable speaker. I'm really looking forward to his talk today. Just with the matter of formalities and format, please use the hands up feature in the GoToWebinar software to put your hand up to ask questions, and we'll unmute you so that you can ask the question directly of Nick. Or you could also put up your questions in writing, either in the chat section or the questions section in the panel that you have in front of you, and one of us will ask Nick those questions that you've posted. I'm supported by Sarah Salwe, our General Manager Member Engagement, and Imran Hussain in the background. So thank you very much for that. Thank you very much again to the Frontier SI partners who have helped make this real. And without further ado, I hand over to Nick. Nick, all yours.
Thank you very much, Anil. Thanks for the lovely introduction. And thanks to everybody for joining the webinar today. Yeah, my name's Nick Brown. I'm the Director of National Geodesy at Geoscience Australia. And don't worry if you don't know what geodesy means, we'll cover that in a minute. This webinar is really around datums and reference frames, and I recognize that some of you may not know what that is. Well, I hope you'll get a bit of an insight to what it is today, but don't worry if you don't know too much about it. This is what we're here for. And if you've got any questions, I'm happy to stop and answer those as we go if anything pops up, or alternatively pop them in the chat and we can have a chat about it at the end. This presentation's really been designed to help you understand what datums and reference frames are, why they're important, maybe answer some of the questions you have about them, and maybe even answer some of the questions you didn't even know you had until we had the presentation today. So, first step, what is geodesy? So geodesy is all about the science of measuring the shape, orientation of the Earth and gravity field of the Earth, and how that changes over time. The Earth's not a static body. There's moving parts, and we need to understand how they're moving if we're going to be able to position ourselves at the sort of centimetre level, which is really our aim here at Geoscience Australia. So the geodesists use a number of techniques to try and develop these reference frames, and we're not going to get into the details of them today, but we need a range of different instruments to measure the spin rate of the Earth, the size of the Earth and how that's changing, and movements, importantly, also in the mass distribution, because the distribution of mass within the Earth is actually what dictates the Earth's gravity field, and that changes over time as well, and we can see that from gravity satellites that are orbiting the Earth and terrestrial techniques that we use to measure the Earth's gravity field. So nothing is constant. We live in a very dynamic world. And none of these measurements can take place unless we have what's known as a geospatial reference system. So the system is actually talking about this collection of datums, reference frames, the infrastructure we need, the models and the standards that we use for four-dimensional positioning. And I'll show you a slide in a minute that sort of covers what the system looks like for Australia and what we consider to be the important parts of that system. I often liken geodesy, talk about datums and reference frames to this kind of quote that came from the chief scientist of Xerox many years ago, and that is that it's the most profound technologies are the ones that disappear. They weave themselves into the fabric of everything in life until they are indistinguishable from it. So a couple of examples of things like that are things like electricity. You plug your phone charger into the wall and you just expect it to work. Nowadays, it's with the internet, having it in your smartphone wherever you are at any given time. And datums and reference frames are very similar to that sort of invisible foundation infrastructure that we rely on every day to position ourselves, align our spatial data in all these different fields, whether it's the environment, society, economy. We're always dealing with spatial data and trying to align this spatial data to make better decisions. So I want you to use your imagination. That's why you've got a grey screen here. I find it helps my imagination. I want you to have a think about you're in a situation and you're asking yourself, maybe you're stuck in a bushfire and you're seeing smoke all around you, and you're starting to wonder things like, where am I? Where are my friends and fellow firefighters? Where is the water around me? Where's the fire truck? Where's the fire front? How fast and in what direction is that fire moving? And where are the houses in this area? So you can imagine that's a pretty dramatic scenario, but I think it highlights a lot of the dependence on foundation data. So if you had a look at it from this point of view, you might be looking at it in terms of what kind of data sets you're going to need to try and answer these questions. You're looking at things like water bodies, you're looking at road infrastructure, you'll be looking at houses, trying to understand where emergency units are and how fast they're moving. And to make decisions based on all these data sets, we need to actually make sure all these data sets are lined up so that we can make an informed decision where we can look through all this information. But what's that based on? What's this question mark down here? You may have read Stephen Hawking's book, Brief History of Time, and in that, one of my favorite lines is he refers to a well-known scientist, and in the book he says, some think it was Bertrand Russell. He once gave a public lecture on astronomy, and he was describing how the Earth orbits around the sun and how the sun in turn orbits around the center. And then he talked about this vast collection of stars in our galaxy, and at the end, he said in the end of the lecture, a little old lady stood up at the back of the room and said, "What you've told us is rubbish. The world is actually sitting on a flat plate supported on the back of giant tortoise." And the scientist gave a smile and said, "Yeah, but what's the tortoise standing on?" And she said, "Oh, you're a very clever young man." But the old lady said, "But it's turtles all the way down." So the way that I like to think of the Earth is that it's what we've learned recently, and modern technology has actually taught us that it may not be a stack of turtles that we're sitting on the Earth that's allowing us to line all our data. But if you ask me, it's something even more magical and more complex. We on Earth, we're sitting on the third rock from the sun, and the sun's hurtling through space, which is not something people often think about. But if you think about the sun, a star is actually moving with respect to galaxies. They all then have their own gravity field, and you've got planets and moons all orbiting each other as the sun's traveling through space. And from that, we are able to define a coordinate reference frame or a datum that allows us to position ourselves still at the centimeter level and understand how things move dynamically through time. So that data and information is collected on a whole range of different scales. And then we put all that data together to develop a reference frame or a coordinate reference system for the Earth, and then importantly, one for Australia. So that alignment of all this spatial data that I'm talking about needs some sort of reference system. You need datums, you need a reference frame that's moving with time. You need standards which allow you to talk to other data sets and align your spatial data in software. And in Australia, this is known as the Australian Geospatial Reference System. So to talk you through the elements of what that looks like, as I mentioned, the system is actually the collection of all these different elements. And I don't want you to be too overwhelmed. We're not going to go into the details of all of these today, but it's useful to think of the ones where we've got the white box with the blue outlines. They are the datums or the reference frames that we use in Australia. And you may have heard of some of these before, with in particular things like GDA 94, which is a geocentric datum of Australia from 94, and the newly introduced geocentric datum of Australia 2020. These are static datums. So the static references for latitude, longitude, and height that don't move over time. But the Australian plate is moving at 7 centimeters a year, and there's some users who actually need to take that into account. So for that reason, we've recently introduced the Australian Terrestrial Reference Frame 2014, which actually is a coordinate reference system, so lines of latitude and longitude that move with the Australian plate as it moves at 7 centimeters a year to the northeast. We also then have these blue circles here, which are the models that allow you to move between different reference frames, whether you're working in the static one or the time-dependent frame. And then on the right-hand side, we'll touch on a bit later on what we use for height datums in Australia. I mentioned before that gravity plays a really important role, and in these datums like GDA 2020, you get a height with respect to a simplified representation of the Earth called the ellipsoid. But water doesn't flow according to the ellipsoid. Water flows according to change in gravity. So we need these gravity-based height datums, which you use on the right-hand side. And I'll touch on that in a little while. So in what I like to call spatial awareness, we're talking about these changes that we've made to reference frames and datums in Australia. And the question is, why do we go to the effort of actually updating these reference frames? The best way to think about it is that your datum, so your reference frame for latitude, longitude, and height, that datum is not free of error. And over time, errors increase in things like datums, so we need to refine them. And also the positioning technology we're using gets more accurate and user requirements get more accurate. And given that your datum always needs to be more accurate than the data, we reached a point where we knew that in the very near future, the users are going to have accuracy in smartphone technology or in their car that's sort of going to be at that centimeter level. And we knew that previous datums we'd used in Australia had errors that were sort of in the 0.5 meter type range. So we needed better datums to enable the users to use their very accurate data. And here's a sort of a brief summary talking about where they predict. You think about the GPS chipsets that sit in your smartphone or any other different technology. Where are those chipset sales going in the very near future? Who's buying them up? And the traditional markets of users of GPS information from maybe the surveying sector or the agricultural industry, you can see are predicted to make very small, make up much smaller amounts of where the chipset sales are going to go in the future. And instead, there's these massive markets of location-based services with mobile technology and the intelligent transport sector. So we're looking to more and more stages along that route of having autonomous vehicles. So this is a very big change in the positioning technology. It's therefore a big change in the users of the datum. And we needed to make sure that we had a datum that was accurate enough for those users. You may recall from previous presentations, for those of you who have sat in, Chris Marshall from Frontier SI in particular gave an overview of the Positioning Australia program that we're working on at Geoscience Australia, and Frontier SI is helping us out with. And just to cover it off in one slide, what I wanted to show you, for those of you who didn't see Chris's presentation, is that this is potentially, this is the way that users will be accessing this data in the very near future. So we have these, down the bottom left-hand side, you can see some stations, they're ground stations, and they're picking up signals from, these would be GNSS satellites, which are orbiting the Earth, and that's providing positioning information down to these static base stations. What we do from these sites is we know where they are very, very accurately. So we use the information that's coming down in real time to compute corrections in the atmosphere, corrections to orbits of the satellites, and also any clock biases in the satellites or in the receivers. And we send all that information through to a processing correction facility. And then what we can do is deliver corrections either via the internet or via an SBAS satellite. And what that's going to allow us to do is transmit those corrections to those user groups shown in the middle to take the accuracy you're currently getting out of your GPS receiver, which might be at sort of the 5 meter level. And that's going to bring it down to somewhere between 3 and 10 centimeters throughout all of Australia and its maritime jurisdiction. So this is a real game changer in terms of the positioning capability that we're going to have enabled in Australia. So keeping that in mind, the user's going to have, 10 centimeters or better accurate positioning capability. If you then have a look at the previous datum we used to use, the lines of latitude and longitude, you can see that we had a few things to contend with. The first thing is that between 1994, which was where the old datum was in Australia, we're effectively moved the Australian plate about 1.8 meters since that time. So a user getting a signal from GNSS is going to see a very different position that they would have seen if their data was stored in GDA 94, where we're assuming the Australian plate is about 1.8 meters southwest of where it was. So we've got these large movements of the plate. And then we also had these localized distortions and biases. If you have a zoom in look at an area within New South Wales, due to the way the 1994 datum was implemented, since that time, we've been able to work out a number of biases and distortions that were in that network. What we wanted to do was remove those so that and these errors are up to about 0.5 meter. They're very difficult to model accurately. So we were better off generating a new datum that was free of a lot of these biases and distortions, so that users would have a much more accurate reference frame, which is GDA 2020, and it would be very closely aligned with what they're getting out of their GNSS receiver. This is to show you some of the really fun maths that we get to do to compute some of this stuff, and the fact that we also go through a process with the National Measurement Institute to get these new coordinates and new datum recognised under the National Measurement Act. So Geoscience Australia takes on that role of computing what the datum is, and then we liaise with the National Measurement Institute to get that recognised by Commonwealth law. And then that becomes something that the states and territories can refer to and then update their databases with the new coordinates. So we've sort of briefly touched on that middle section of the upgrade that we've made to the static datum. The bit I wanted to quickly touch on now is why do we bother having that time-dependent reference frame? Why do we have a positioning reference frame that's moving with the Australian plate? And one of the best examples I think of is things like Strava, right? So everyone loves getting down their Strava times. I'm not a cyclist myself or a runner, but I have a lot of friends who really think this example sits with them. And if you picture yourself as being getting Strava out and you're getting 10 centimeter accurate positioning through a service within Australia, what you really want to do is you want to be able to align the maps that you're getting from straight from the internet in the reference frame that's going to align with the 10 centimeter accurate data that you're getting from an SBAS satellite or from over the internet. So a lot of information now is being served up to users in real time. Some of you may have heard of the International Terrestrial Reference Frame, ITRF. Effectively, that's modeling the Earth and how it changes over time, and it's always giving you information based on where your location, where you are right now. And so with respect to the Australian plate, some people want to be able to model the movement of the Australian plate so that they can line up all their spatial data very, very accurately in real time. And for those types of users, that's where a time-dependent reference frame is going to be really useful for them. The other key drivers for things like this are things like autonomous vehicles as we move through those stages, as I mentioned before. Maps are going to be fed to users in real time, and the positioning information they're going to be getting from GNSS is coming through that international terrestrial reference frame, which in Australia will be delivering as ATRF. So it's very, very much aligned with ITRF, but as I mentioned before, we have that connection back through to Commonwealth legislation or Commonwealth law, which shows how the Australian terrestrial reference frame can then be legally defined and legally traceable. But it's very much the same as the reference frame that the GNSS satellites are operating in. So to move between GDA 2020 and ATRF, what we've developed is what we call a plate motion model. We're fortunate in Australia that the Australian plate moves very much as a stable plate towards the northeast at about 7 centimeters a year. So what we've developed is a model that allows us to move coordinates with time, so that they can update their coordinates and move it with the Australian plate. So for anyone who's interested in looking at from a software development point of view, we have like Python packages and things that we've developed that'll allow you to take these parameters that we've got down here, and it'll effectively allow you to map data back and forward through time between GDA 2020 if you're in a static datum, or if you want to work in the ATRF 2014, you can map that data forward using the plate motion model. We're lucky that we can just use a very simple model to move our coordinates in a direction. Countries like New Zealand, who we work with on the development of things like deformation models, they need to use deformation models to map their coordinates back and forth through time to handle the earthquakes that they have to deal with. So our solution in Australia is a very much simpler option. So here's just a diagram that sort of shows how that works. On the scale we have on the y-axis, you can see you've got a change in position, and then on the x-axis you have time. So as you go through time, you'll see that GDA 2020 coordinates, they don't change. You're always making that assumption that the Australian plate isn't moved and that it's locked to the position it was in 2020.0, so the 1st of January 2020. And that's exactly the kind of reference frame that certain people like surveyors are particularly interested in, because they don't really want the coordinates of points to change over time. But if you're working for an autonomous vehicle company, you really want to be working in ATRF 2014. You want to be mapping the exact location of the Australian plate and the position that a user will be receiving in real time. So the plate motion model is going to allow those people to move back and forward through time, make sure all the spatial data sets line up, and allow them, importantly, to work in the reference frame that they want to work in. That was the big driver for us. The next bit I'll touch on is the stuff on the right-hand side. I've only got a few slides left, and then hopefully we'll still have plenty of time for questions if there are any. So this is the really fun bit. When I did a series of webinars on changes we'd made to the reference system last year for some of the users around Australia, and the fourth webinar that I gave was around height, and it's essentially was called Height is Hard. You need to be thinking about more than just a geometric surface. So for example, here we have a representation of what an ellipsoid would look like. And if you're computing a position using GNSS, what you're doing is essentially computing a height above or below that very simple representation of the Earth, of an ellipsoid. It's really simple, it's precise, which is fantastic. It's useful for GNSS applications. But when you get into specific heighting applications where you need to be guaranteed that water will always flow downhill, that's where you need to introduce your thinking about gravity. And for that, we use a different reference system. We need something that's based off gravitational potential, which unfortunately is complex. It's harder to define, it's harder to explain. But if you get it done right, then you can always be sure that on that surface, water will always flow downhill. And here's a representation of what that surface looks like globally. And the way that my university lecturer used to describe it, he used to comment that the shape of the Earth's gravity field is like an oddly shaped potato. So it's by no means simple. It is complex, but it necessarily needs to be, because the distribution of mass within the Earth is very different, and it varies depending on your location. So having a very accurate model of the Earth's gravity field is particularly important for many positioning applications. So here's an example of how we get around this within Australia. As I mentioned before, from GNSS, you'll get the ellipsoidal height, which is green. What we then do is we have a model of the difference between that ellipsoid and our nationally recognised vertical datum, which is the Australian height datum. So this model that we use to allow you to convert from an ellipsoidal height to an AHD height is called AusGeoid. So we generate a model of what that offset is throughout Australia, and it allows you to then work in GNSS and work with GNSS, because it's a really efficient way to collect spatial data, and then you can convert it into something that can be used for height determination and water flow, and convert your ellipsoidal heights into AHD heights. So this is particularly important for things like construction and engineering, large-scale irrigation. We've had examples of major road development where it's been shown that if it's not done correctly, it can cause massive changes in the flow of water and actually causes a multi-million-dollar impact on major roads projects if the height datum isn't correctly accounted for. It's also really useful for things like location-based services and also environmental monitoring. You think about large-scale LiDAR surveys that are done throughout different areas, and then you're trying to convert that LiDAR survey into understanding a drainage pattern throughout a region, for example. In those areas, you really do need a very accurate height datum. So here's an example of the current state. We have an Australian height datum. It was introduced in the early 70s on the Australian mainland and introduced in the early 80s in Tasmania. But the two datums together we refer to as AHD, the Australian height datum. How that datum was defined is they took the sort of average of mean sea level from about 32 tide gauges around the country and held that mean sea level fixed, and then did a certain amount of leveling. You may have seen surveyors out there on the road. What they're doing is understanding the difference in positions and heights between different ground marks. That was done over 200,000 kilometres throughout Australia. They did 200,000 kilometres of leveling to compute the change in height in different areas across Australia. And then they throw all that into one big mathematical adjustment and compute the heights all around the country. From that, what we've then done, over time, we've had a whole series of different AusGeoid models that have allowed us to model that offset between the ellipsoid and the Australian height datum and provide that to the user. One of the difficulties we have, though, with the Australian height datum is that due to the fact that the leveling was done so long ago, the way that mean sea level was defined and things like that, we have an uncertainty in the AusGeoid model of about 8 to 13 centimetres. So for some users, that's becoming a bit too large, and if they're trying to model something at the centimetre level, let's say the 3 to 5 centimetre level, they're sometimes very unsure whether the error they're seeing is in the data or is it in the datum itself. So we have been doing some work recently to try and improve the Australian height datum. And what we've found is that we are more than likely looking towards the future where we may introduce a different national height datum. So at this early stage, we've gone some way along that path to moving away from the Australian height datum for some users and introduced an alternative, which is known as the Australian vertical working surface. And essentially it has a lot of the same data that went into producing the AusGeoid models goes into the Australian vertical working surface determination, but we strip out a lot of the leveling type issues that we had in there before. And what we've seen is that we can get the accuracy of the AVWS model down to something like 1 to 8 centimetres, depending on where we had really good gravity data and where we don't. And this is a lot better than what we were seeing with the AusGeoid model, which is accurate to 8 to 13 centimetres. As we collect more and more gravity data, for example, airborne gravity or terrestrial gravity around the country, we're going to drive down the uncertainty of that model. And it means that people who are out there, let's go back to our LiDAR example. If you're a large-scale LiDAR survey operator and you're trying to convert your ellipsoidal height GNSS-derived LiDAR information to something that we can use to model water flow, you may prefer to use the Australian vertical working surface as opposed to AusGeoid, because you're going to be guaranteed that you'll get that higher level of accuracy. Excuse me. All right, now onto the fun stuff, standards. This is really how we always get people excited about standards. I like to try and lighten the mood a little bit, and this is partly in jest, but I also very strongly believe that this standards work that we're doing really is a big deal, and it does need a lot of time and effort dedicated to it. And the reason for that is because we think back to the way that geodesy data has been used in the past. It's been very much driven by a scientific community working on scientific problems. So what it means is that formats and the standards they use for delivering geodetic data to other people, they were usually sharing it with the scientific community. Nowadays, the people who need it are you and I in real time, whether you're in a car, using your mobile phone, whatever it might be. The standards that you need to convert and transfer that information to a user are very different to what they used to be. So there is internationally, there's several working groups working on defining the standards for geospatial and geophysical data, but there's really no, what I'd say is an international strategy to make sure we're driving towards that findable, accessible, interoperable, and reusable data. So what we've done, we've started to look into different sectors and different industries. So for agriculture, for example, we've recently finished a project with Frontier SI, and many thanks to Ivana Ivanova from Curtin Uni who led this. What she's doing is she's looking at what are the requirements for the ag sector. So whether it's accuracy, availability, integrity, coverage, and reliability, we could unpick what they need. We then looked at what standards currently exist to support those requirements, and then importantly looked at the gaps that are in standards. What are the things that the standards currently don't deliver that a user is going to need? And then so we've identified the kind of work that we need to do with the international standards community within ISO and OGC to make sure that once we're providing a signal from our Positioning Australia services, the users on the far end are actually going to be able to pick it up and use it in the way that they need it. So we've done this across about 10 sectors. I've just shown here a couple of slides of different ones. As you may see here, you see it maybe still have accuracy and availability requirements like agriculture sector does, but the accuracy and availability requirements might be different. They might be to a higher standard or have a lower latency. So we've been trying to break down each of these sectors on their own to look at their individual requirements. And a big part of the project we're working on now, so there's public stakeholder engagement work being done now with these sectors. We've done a bit of outreach into these areas. So I'd definitely encourage anyone here who's interested in being a part of that to please follow up with me, and I can send you the information. Whether it might be the mining sector in particular or resources, we're happy to talk to you about what your requirements are to make sure that you can take advantage of the precise positioning that's soon to come. And this is just a bit of a shout out on the Geodesy ML work that we've been doing. This is really looking at how do we fill the gaps that are in international standards. So we don't want to go and reinvent the wheel and develop new ISO and OGC standards. What we want to do is recognize if there are any gaps where they logically can't answer the question or address the metadata requirements we have. We've introduced what we call an application schema, where this is meant to capture or catch all the bits of the metadata that aren't covered by those ISO and OGC standards. And essentially you can bolt this onto it. You could bolt Geodesy ML metadata requirements on underneath to capture all the information that our users are gonna need and make sure that we can transmit that data to the user at a machine-to-machine level without them even knowing that it exists. This sort of work should be abstracted from the end user, but in order to do that, we need to work with the software developers and the standards providers to make sure that it's sitting in the back end of whatever device people are carrying around. And then just to add on to that, we obviously work with the ISO and EPSG Codes communities to develop the standards. So again, it's sitting in the back end in the software. Don't worry, there won't be a test on all these models at the end, just for information. Wanted to finish on a really high note, and that is around some work that we within Geoscience Australia and in particular the Asia Pacific community have done recently, and that is that there was a General Assembly resolution adopted in 2015 around the recognition that geodesy underpins much of what we do. And there needs to be an effort made to sustain a lot of the geodetic infrastructure in many particular countries, and to change the way we think about geodesy from being a scientific, esoteric science into something that is more mainstream and supporting a much broader user base than it ever has before. So this was a massive moment. It's the first spatial general resolution adoption that's ever been made. And so there's still continuing work. We have a subcommittee on geodesy who's continuing to push this narrative throughout the United Nations, and it's great to be engaging with people internationally to try and assist them with their requirements for geodesy in their country. Yeah, it's just been a great initiative that we've been able to be a part of. So in summary, as I said, geodesy and datums and reference frames, I really no longer consider it to being a niche or esoteric science. It's mainstream and with good reason. It's really providing a strong foundation for very good decision making. And the upgrades that we've been making to components of our reference system in Australia are really around driving change, not for change's sake, but to ensure that we're meeting the needs of the user community and the changing user community. and we're hoping that we can ensure that users will get maximum benefit of the Positioning Australia program once it's realised. Obviously, we don't do this alone. We do this through collaboration with the states and territories. And as you'll notice today, I'm not using a Geoscience Australia slide deck. This is really a Intergovernmental Committee on Surveying and Mapping. So I'm talking about the collaboration we have with all the states and territories around Australia. And now, importantly, also within the international community. And that's really keen to ensuring that we get a good product, because you can't create a reference frame for the globe by one country alone. You need to be collaborating internationally. So that's all from me. I'm happy to take any questions, and thank you for listening.
Thank you so much for that, Nick. That was a fantastic exposition on the details of geodesy that goes behind establishing the change in datum and why that's required and how it practically affects us both in our industries and also personally and individually. Your case about cyclists being a good example of that, but also I love the example that you used right at the outset with the fire example, which shows the power of the contextual use of positioning data to keep us safer. It's absolutely fantastic. As a geologist, I also appreciated how the knowledge of global plate movements influenced this whole science, and how the study of these datums also help us learn in reverse more about how the Earth works. So, you know, that sense of collaboration that you have brought, international collaboration between the sciences and between bodies across the globe, is a fantastic model that we can all certainly learn from. Your talk also highlighted the science and technology that supports society in the background, things that we take for granted but know nothing about, but are essential for our modern living and work and safety, what in Amara Global we like to call the invisible infrastructure, which requires a much larger recognition than it does. So I do appreciate how you were ginger about, you know, showing the dryness of part of the subject, but also highlighting the practicalities, the usefulness, and the importance of this. So thanks, that was really good. It's also fascinating to see how expectations have changed over the decades. When I started as a geologist, you know, plus or minus 30 on a meters, that is, on a GPS was pretty good. And there was selective access to at that time, I remember, whereas now 8 to 13 centimeters is not good enough. And but also, I think so importantly, as you pointed out, there's that focus on standardization, there's the focus on the FAIR principles, and seeing geodesy, ML starting to play a part, I think is going to change how we look at and how we work with spatial data. And lastly, also, congratulations on the recognition received for geodesy at the United Nations. That is really fantastic to hear.
Yeah, thank you very much. It's I think that the multidisciplinary bit that you touched on is extremely important. We learn a lot here at Geoscience Australia just by sitting in the same building as people who've got very different backgrounds. I mean, we're obviously in the positioning space, but we work with experts in geology and geophysics and earth observation, a whole range of different sectors. So it's good for us to be able to just walk around the corner upstairs and ask someone in a different field, how would you tackle this problem? Because we've never dealt with it before, but I think we're going to have to do it more and more. So it's I'm fortunate to be within Geoscience Australia where we have that capability.
No, I absolutely agree. I mean, that's one of the strengths of having something like Geoscience Australia, to working towards our national interests, which is and internationally. That is, it's a brilliant model, and we look forward to more work and similar seminars that educate perhaps the educated lay people who are in the audience today, and also the people involved in this science. So I do encourage people to ask questions. I think Chris, to begin with, Chris Marshall has a question. I can unmute you, Chris, for you to ask your question. Can you please go ahead?
Sure. Thanks, Neil, and great presentation so far, Nick. Yeah, you really make those topics seem accessible. Geodesy can be quite impenetrable for some people, so really great. I just had a question around the ATRF 14 and the GDA 2020. You mentioned there's the dynamic datum and there's the static datum there. So how, what sort of tools are available for sort of automation and working between those two data sets? Because I know that's going to be a problem for some organizations.
Yeah, that's right. It's a good point. The first thing I often like to tell people is that if you don't have a really strong need to be working with a dynamic datum or a time-dependent datum, then don't. It's really out there for those users who need it as part of their business to make sure that data is fit for purpose for the user. So that's where it comes in with location-based services and intelligent transport. They're the sectors that are going to be having to know exactly where a user is and exactly where the Australian plate is at any given time. So for those sectors, particularly because those new sectors who need to understand that may not have a very strong understanding in geodesy or geomatics, what we've done is we've got some online tools that you can use through the GA website that help you understand how it works and allow you to check what you might be doing. But we've also developed a Python package. So we have a package called GeodePy, which is you can get through GitHub, and effectively that's what all our tools and services are based on. But that's the back-end Python package that software developers can pick up and adopt and be confident that it's come from us and we've checked it. Always happy for them to check it as well, and if they find anything, please let me know. But so far so good. I think we've got the package right.
Thank you. I think Mahesh Thapa has a question. Mahesh, do you want to speak up and ask your question directly? You're muted. No? Okay. If you do want to ask a question, just unmute yourself and speak up, please. Nick, I had a question for you. I mean, we've been through this before, the shift in datums, and I remember as an exploration geologist, when the transition took place to GDA 94, we were plotting maps that were 20 meters out. And that took, at that point in time, in the mining industry particularly, I think it took a while to get ready for that change, and so there were a lot of disruptions that happened. So in terms of the 2020 datum and the change in the AHD potentially, what do users in the resources sector need to do to prevent that same disruption when the new datum is available? What do they have to be aware of, and what are the kind of costs that's going to be involved in this?
Yeah, excellent question. Since we started this process in the sort of around 2012 or around that time, the first thing that we were keen to do was to start talking with some of the larger companies who might be impacted by the change, and some of those were resource sector companies. The short answer is that similar to the answer I gave before, we're not enforcing a change. What it comes down to is client and customer requirements. So what we're finding is that there are some major sectors where centimeters start to matter. And in that case, it's almost in your best interest to be moving to a more accurate datum to make sure that your data lines up. But having said that, there's also a whole range of sectors where we know of when we're talking about acreage releases off the coast of for offshore petroleum exploration or minerals exploration licensing. where the boundaries are actually still based in AGD 66 or AGD 84, and they probably always will be. So in those cases, where it's fit for purpose, we're not imposing a change onto anybody. I suppose what we're doing is we're upgrading the datums we have in Australia and the services we provide for those who need something more accurate. But the legacy datums that we've created and still exist, if they're still fit for purpose and it suits your client requirements, then there's really, it's really up to you, and it's a business decision as to when you move. We at Geoscience Australia, me personally, I'm happy to help talk anybody through these kind of discussions if they're thinking about it internally and they want to walk through how it might benefit and what are the cons associated with it. We've done that with a lot of organisations and companies, and in some cases you find they don't need to change, and in others they find they might want to change one part of their business model, but they'll leave some of the other stuff working in an older datum, and that's fine.
Okay, no, that's wonderful. So I take it that the vendors of software, GIS systems and stuff will automatically adopt and provide that ability to convert to or operate in the new datum, and you'll be working with those companies, or they'll have access to that to update those products.
And that's an excellent point. We do a lot of our work with the software companies so that the end user can almost just click a button and the changes will happen for them. So we're hopeful, we've already seen it flow through a number of software companies who have made the updates that are required. We're still working with others. And if there's any out there who haven't adopted changes to Datum that you'd like to see, then feel free to let us know who they are. And we're happy to touch base with them and see if they've got a strategy to implement the new Datums.
No, that's wonderful. Now, there is one more question from Mahesh that's been posted on the questions side of things. I just need to be, I'm having some problem trying to get it up. Just give me one moment while I look for where my questions panel has disappeared. Imran, can you help me out? I can't find my questions panel. It seems to have disappeared.
That's okay. Can everybody hear me?
Yeah.
Okay. The question that Mahesh had, and I'll read it verbatim. When the datum is updated, how is the data based on previous datum, such as cadastral maps, managed? Are all of these updated with some kind of transformation?
Yeah, excellent question. So all the states and territories are the organisations who are responsible for cadastre, and each of them in one way or another are going through a process of updating their state-based legislation to recognise GDA 2020, for example. As part of that, they're also updating the software that sits in the back end, and they're doing transformations of all the cadastral boundary type information into the modern reference frames. So it's all the state and territory bodies who are working on that, and I'm sure they'd be more than happy to have a chat with you about how they're doing it specifically within their jurisdiction.
Thank you. Were there any more questions?
Yes, there's a couple more from Eric Baran. Perhaps explain the WGS 84 issue. And Eric has also made a comment. Western Australia has transformed cadastre to GDA 2020 and maintains cadastre in GDA 2020.
Yeah, thanks. Eric's one of the great people I was talking about who is part of this ICSM community. So Eric has been the sort of state-based representative who's played a big part in developing GDA 2020 and then implementing that within Landgate, within WA. So that's my credit to Eric. Now to touch on his question around WGS 84. Yeah, this can be a tricky one because WGS 84 is often used within software. It's kind of a default option that can exist within software or web services. And in some people treat it as a static datum that's based at a particular epoch, whereas in reality, WGS84 coordinates are actually, they're very much like the ITRF ones or ATRF ones I described. They're actually giving you a movement of the Australian plate as it's changing over time. So WGS84 is a time-dependent reference frame. So it's very closely aligned with ITRF or ATRF that I've mentioned. And it's always useful to dig into the metadata a little bit when you're getting access to data that's in WGS84. You want to know what assumptions that user has made. Is it fixed to a particular epoch, or is it treated as a time-dependent reference frame? So it's very specific to the data set when you're looking at WGS84. And yeah, anyone who's using that, I'd encourage you to have a chat with the data provider to better understand when it was captured and which epoch it refers to.
Nick,
Thank you,
thanks
Nick.
very much. Sorry, was that you, Imran?
Sorry, that was Imran. There are no more questions, but if there are any more questions, feel free to type them in chat or put your hand up and we can unmute you. But I'll leave it for Anil and Nick.
Thank you. I think we're nearly running out of time. Nicholas, thanks so much for your presentation. I found that incredibly useful to have that language translated into something that can gather common understanding is so important, and you're doing that really well. So all the best to the work that's going on in Geoscience Australia by you and your team. We look forward to keeping this connection and look forward also to the participation of yourself and the audience at the workshop next week, where the idea would be to bring together the community of users as well as service providers and researchers and talk about what there needs to, what are the challenges and opportunities for the future, both in positioning and the use of positioning data, and how we go forward to better support and enable the industry to use this data effectively and for greater productivity. So again, thank you all for attending. Thank you to Frontier SI, and thank you, Nick, for your excellent presentation. And we hope that we'll catch up very soon. Thank you.
Thanks, Anil. I look forward to seeing you all next week. Bye.
Yeah, thank you.